The next piece of the puzzle is, what are the possible locations for an absolute maximum or an absolute minimum? I'll talk primarily about maxima, and all you have to do is turn your picture upside down, and you're talking about minimum there. So I have a picture here, and we have an open interval from A to B. We have this graph going from these values here from A to B. Now, a key notion is this: not all functions, not all intervals. You do not always have an absolute maximum, absolute minimum, or even a relative. There might not be any extrema. There might not be any maxima or minima. There might not be any extrema. This is a case where there are no absolute max, there are no absolute min, there are no extrema on this picture. Now, it's not too challenging to see. A person might say, well, wait a minute. What about this point that's very, very close? But remember what this picture is supposed to represent. If I take a point that's very, very close here, remember, if I zoom in on this picture, what I actually have is this. And this is the point you chose that's very, very close if I magnify my picture. And now that's clearly not the maximum value, because look at all these possibilities. And then you can say, well, yeah, what about that picture point right there? Well, again, simply zoom in on the picture. And now we have that, which means all these points are higher than the point in question. So as long as this is not included, see how this is an open interval? If this endpoint of the graph is not included, in this case, there is not necessarily a maximum value. Similar, and the same argument goes here, right? If you zoom in here, we actually have this picture, and there are lots of other points we could choose. And if we choose a point very close here, we could zoom in on that part of the picture, and we have other choices we could select. And so if the endpoints are not included, there is no guarantee that this maximum or minimum value actually occurs. It might occur that way. It could happen that we have a picture like this, but that's not a guarantee. You just got lucky because this is coincidental with the graph you're talking about. If we just randomly select a function and we do not include the endpoints for this graph on this interval, if we just randomly choose a function and if we do not include the endpoints of the interval, then we might randomly select this one, and there's no guarantee there's going to be a minimum or maximum value. It might happen, but there's no guarantee. And so, we get the following notion. We get the extreme value theorem. We get the extreme value theorem. It says this: if f of x is continuous. One of the reasons we studied continuity so savagely back in chapter 1 is because continuity is what's going to guarantee that all this stuff, remember chapter 3 is using derivatives to do things. In order to have the derivatives do the things we're saying, we need to have continuous functions. That's why we talked about continuity way back when in chapter 1, so in detail. If f of x is continuous on, and here's the key, on the closed interval AB, it must be a closed interval and it must be of finite length. If the interval you're dealing with is from A to infinity, then all bets are off. It might happen, might not. We don't know. I'm not saying anything about that. Might work, might not. If it does work, you just got lucky. If it doesn't, well, no, I didn't say. So if this is the interval, we cannot make any statement about this kind of an interval. We cannot make any statement about this sort of an interval. We cannot make any statement about this sort of an interval. The only time this theorem applies is if we're talking about a continuous function and it must be on a closed interval of finite length. in this case, non-zero finite length, a non-zero finite length for our purposes. If f of x is continuous on this closed interval from a to b, then there must exist c in the open interval such that f of c is, well, we'll say f of c is less than or equal to f of x for all x in the interval, and there must exist a d in the open interval AB. Closed interval. Such that f of d is greater than or equal to f of x. And again, this is the same. Each of these is for all x in the interval. That's a bunch of words. There's a nice, concise way of saying it. Officially, it says there must exist a c such that c is the minimum, and there must exist a d such that d is the maximum. Minimum, maximum. There must exist a minimum and there must exist a maximum on that interval. If you have a continuous function on a closed interval, there must exist a maximum, there must exist a minimum. Very often what we'll say is f achieves both a max and a min. Now, we'll draw several pictures that illustrate this. All right? So, here's one possibility. Here's A, here's B. Now, we're including the endpoints, right? It's going to be continuous on a closed interval. Here's one possibility. That's one possibility. Does this function achieve a maximum? Yes. Where is the maximum? The maximum occurs at the endpoint. Remember, I wrote this wrong initially. This C and D, the minimum, where the minimum occurs and where the maximum occurs, it could be at the endpoints. It could be at the endpoint. The max and min might occur at the endpoint. So it could be that in this case, C is the minimum. So see, C is the minimum. So C is here. And D is the maximum. D occurs here. So the maximum or minimum might occur at the endpoint. Another possibility is it could be something like this. Here's A, here's B. The maximum might occur at one of the endpoints. The minimum might occur somewhere else. That's a possibility. Here's another possibility. The maximum might occur at a non-endpoint, and the minimum might occur at a non-endpoint. Here's another possibility. We could have a function that comes to a point. Here's A, here's B. Now this function is continuous. Remember what continuous means? Continuous means there are three things you don't have. What three things do you not have for a continuous function? No holes, no jumps, no vertical asymptotes. No holes, no jumps, no vertical asymptotes. You are allowed to have a cusp if all you're requiring is continuous. In order to get rid of the cusp, you would need to add the extra requirement of being differentiable. Differentiable means the derivative always exists. So differentiable means also there are no cusps. But all we have now is continuous. No holes, no jumps, no vertical asymptotes. So as long as you connect these 2 points with a continuous curve, no holes, no jumps, no vertical asymptotes, there will be a maximum. In this case, the maximum happens to be at one of the endpoints. In this case, the minimum happens to be at one of the at a point in the interior. So any mix is possible. Remember, endpoints are a possibility, or the interior is a possibility. Now, another piece of terminology, each of these points, that value, those values, and that value, each of those is called, has a special piece of terminology here. There's a terminology for everything. Each of those is called a critical value. So here, the endpoint, the maximum occurs at the endpoint. Here, the maximum occurs at the endpoint. Here, the maximum occurs at the critical value. Here, the maximum occurs at the endpoint. Here, the minimum occurs at the endpoint. The minimum occurs at a critical value. Minimum occurs at a critical value. Minimum occurs at a critical value. And it turns out that is a requirement. If I have a continuous function on a closed interval, continuous function on a closed interval, extrema so if f of x is continuous on the closed interval AB, if f of x is continuous on the closed interval AB, extrema must occur at either critical value, and we'll talk more about critical values here in just a moment, critical value or an endpoint. If a function is continuous on a closed interval, if it is not continuous, this statement is not necessarily true. If it is not a closed interval, it's not necessarily true. If it's not the closed interval AB, it's not necessarily true. But if it is continuous on the closed interval AB, then the extrema, number one, the extrema must exist. There must be a maximum. There must be a minimum. There might be more than one. There might be. Remember, we saw our trigonometric curve. We had two values where the maximum occurs. There were 2 values where the minimum occurs. It might occur more than one place, but it must occur somewhere. There must be a maximum, there must be a minimum, and those values may only occur at either a critical value or an endpoint. What we're going to be doing is searching to find the extrema. Searching to find the extrema. We need to find the maximum. We need to find the minimum. Where does the maximum occur? Where does the minimum occur? What is the maximum value? What is the minimum value? We need to find them. And the search begins with the critical values and the endpoints. We specify the endpoints and we identify the critical values. More on that in a moment. But that's the issue. In order to find the maximum and the minimum on a continuous function on a closed interval AB, you need to find the endpoints, identify the endpoints. That's easy. They're given or implied in the problem. Then you find the critical values. We'll talk about that. And then those are the candidates that you need to check out to find where the maximum value and the minimum value are located and what are the maximum and the minimum values. All right? So that's a sketch through of the terminology, and now we're going to take a much closer look in our next videos about this notion of critical values and what that portends.